Welcome to the Lecturio podcast. You spend hours learning anatomy, you practice mastering your bedside communication, and then out of nowhere, you are hit with a math test.
Right, and it's not just a casual pop quiz either.
No, it is a dosage calculation test that you must pass before you are even allowed to step foot on the clinical floor. That infamous math phobia is just incredibly common. But, take a deep breath because you're definitely not alone in feeling that apprehension.
The math might seem intimidating right now, maybe even a little dry when you were just staring at it in a textbook, but it is the most crucial tool a nurse has to guarantee patient safety.
Which is the mission of this deep dive. We're going to look at the basics of dosage calculation, ratios, and proportions, and, we're going to break them down into light, manageable steps.
Love that.
Yeah, we want to give you a balance of the theoretical math and the practical, real-world bedside tips so that you feel completely prepared for clinical practice. No more panicking when you see fractions on a test.
That sounds like a great plan.
So let's start at the very beginning. Before you mix any medications or drop any liquid into a syringe, you have to know who you are treating. Finding a safe dose is almost always based on body weight.
Yes, it is.
So we really need to talk about weight conversions.
That is the foundational step. In some areas of adult medicine, you might see doses that are somewhat standard across the board.
Right.
But especially in the pediatric population, so neonates and infants dosing is heavily, sometimes entirely dependent on the patient's weight.
Which makes sense, yeah.
And those tiny patients are almost exclusively weighed in kilograms, which you will see abbreviated on medical charts as kg.
Okay.
Yeah, and just to give you a mental baseline, 1 kilogram is equal to 1,000 grams. Now, adult weights might be charted in either pounds, abbreviated as pound, or in kilograms, depending on, the triage nurse or the specific facility.
Which brings us to the famous 2.2 rule. This is your best friend for weight conversions.
It really is a lifesaver.
Yeah, to convert pounds to kilograms, you just divide the weight in pounds by 2.2. And as a fun side note, dividing by 2.2 makes a person's weight look much, much lower on paper.
Oh, totally.
So if you ever want to feel instantly svelte, just calculate your weight in kilograms. On the flip side, if you need to convert kilograms back to pounds, you just multiply those kilograms by 2.2.
It is a handy trick for feeling lighter. But in the clinical setting, mastering that 2.2 conversion is a non-negotiable skill. I mean, you will be doing it constantly, often just in your head while walking down a hallway.
So what does this all mean? I have to ask, since America mostly uses pounds in everyday life, why the heavy reliance on kilograms in the hospital?
That's a good question.
I mean, doesn't translating a patient's weight into kilograms just introduce a whole new opportunity for a math error? Why not just chart everything in pounds and save the nursing staff a step?
That is a very fair critique, and it is something a lot of nursing students wonder.
Right.
The reason we use kilograms is that drug doses are calculated in highly specific increments by the pharmaceutical manufacturers themselves. When you read a drug handbook, you're usually dealing with micrograms or milligrams per kilogram per day.
I see.
Kilograms are the global standard for science and medicine. The hospital runs on the metric system to maintain universal safety standards, basically creating a unified language for every single healthcare professional in the building, from the physician to the pharmacist, right down to the bedside nurse.
Okay, I hear that. But what happens if someone slips up and uses pounds anyway?
Well, that is where the real danger lies. If a doctor orders a medication based on a patient's true weight in kilograms, and then the nurse mistakenly calculates the final dose using the patient's raw weight in pounds, the patient is going to receive a massive overdose. Oh, wow.
Yeah, think about it. A patient who weighs 150 pounds only weighs about 68 kilograms.
Right.
If you calculate a dose using the number 150 instead of 68, you are giving more than double the required medication. The metric system prevents that chaos, provided everyone is actually speaking the same language.
That makes a lot of sense when you put it in terms of doubling a dose.
Okay.
So we have established the patient's weight, we used our 2.2 rule, and we know our ultimate goal is safety.
Spot on.
But, knowing the patient's weight is completely useless if we don't know the physical concentration of the liquid medication we're holding in our hand. Looking at a drug label with colons and fractions printed all over it can still make my brain freeze. How do we decode the actual vial?
We do that by understanding ratios. A ratio is essentially just a way of describing the concentration of a substance.
Now, before we jump straight into complex drug labels, let's look at this through a highly visual, non-medical example from our source material.
Oh, this is a fun one. Let's talk about Harley the Schnauzer. At its core, A ratio is just a relationship between two numbers. Imagine you are looking at Harley the Schnauzer's toy collection. If Harley has 3 tennis balls, and there are 4 Schnauzers in the room wanting to play, the ratio of tennis balls to dogs is 3 to 4.
Right.
You can write it as a fraction, with the 3 on top and the 4 on the bottom. Or, you can write it with a colon between the numbers, like 3:4.
And just to establish the proper terminology here,
Yeah.
whether you are looking at a fraction or a colon, those numbers have specific names that you will definitely see on your nursing exams.
Oh, for sure.
The number on the top of the fraction or on the left side of the colon is the numerator. In the Schnauzer example, the 3 is the numerator.
Okay, the 3.
The number on the bottom of the fraction or on the right side of the colon is the denominator. So the 4 is the denominator.
3 tennis balls, 4 dogs, numerator, denominator. That is easy to picture.
Yeah.
But going straight from solid objects like dogs and tennis balls to liquid medications feels like a leap. How does a ratio represent a liquid concentration?
That is the critical bridge to cross. Think about how we dilute things in everyday life.
The source material uses a brilliant concept for this, bitter vinegar.
Yes, the vinegar example is great.
Imagine you have a bottle of intensely sour, bitter vinegar. If you pour one single drop of that vinegar into a tiny thimble of water and drink it, it is going to burn your throat. It is incredibly potent.
Right.
That is a tight, concentrated ratio. But what if you take that same single drop of bitter vinegar and drop it into a massive swimming pool of water?
You wouldn't even notice it.
Exactly. You won't even taste the vinegar. The physical amount of vinegar didn't change. It's still one drop. But the ratio of vinegar to water changed drastically.
What's fascinating here is how that exact same conceptual relationship translates into high-stakes medicine.
Oh, yeah.
When you look at a drug label, you will often see a ratio printed right on the vial to tell you how diluted the medicine is. For example, you might see the medication epinephrine with a label reading 1:10,000.
Right.
Using our terminology, the 1 is the numerator and the 10,000 is the denominator. It means there is 1 part active medication to 10,000 parts of solution. It is mostly saline or sterile water with just a tiny bit of the active drug.
Oh, it is like the swimming pool. It is highly diluted.
Yeah, totally. And understanding how diluted or concentrated that ratio is can be a matter of life and death, which, brings us back to the Quaid family case you mentioned earlier.
Right. Dennis Quaid's newborn twins were accidentally given heparin, which is a blood thinner used to prevent clots. But there are different vials of heparin in the hospital.
And this is where the medication label becomes the most dangerous thing in the room if it's misread. The twins needed a pediatric flush, a very, very diluted solution. The standard pediatric concentration for a heparin flush is often something like 10 units per milliliter. But the adult version of heparin, which is used for full-grown adults experiencing major cardiac events, might be a concentration of 10,000 units per milliliter.
That is a staggering difference, 10 versus 10,000.
It is, because the physical vials looked somewhat similar in color and size at the time, and the concentration ratios were not properly verified by the staff, the newborns received the highly concentrated adult-strength solution by mistake. A massive overdose.
Thankfully, the babies survived after intensive medical intervention, but that incident led to massive advocacy for clearer medication labels across the entire healthcare industry.
100%.
An adult vascular system might be able to handle a tight, potent concentration, but a tiny neonate needs something much more diluted. A highly concentrated dose will overwhelm their system instantly.
The ratio tells you the potency. That is why you can never simply glance at a vial. You have to read the numerator and the denominator.
Okay, so knowing a single ratio is great. You look at the vial, you see 1 to 10,000, and you know what it means conceptually. You know how potent it is. But in clinical practice, knowing just one single ratio isn't enough to give a medication. A nurse is constantly having to compare the actual medication they have on hand in the med card against the hypothetical dose the doctor ordered in the patient's chart.
Right, you're always comparing.
To compare 2 different ratios, we have to use proportions.
A proportion is simply a mathematical statement that 2 ratios, or 2 fractions, are completely equal to each other. They share the same relationship.
Okay.
Going back to our non-medical example, if you have 3 tennis balls for 4 dogs, that is the same relationship as having 6 tennis balls for 8 dogs.
They balance out perfectly.
They do. But in nursing math, you can't just guess if they balance out. You have to prove it mathematically using a process that involves the means and the extreme.
The means and the extremes.
Yeah, if you write out a proportion on a piece of scratch paper using colons, like 3:4 equals 6:8, The means are the numbers sitting right there in the middle, closest to the equal sign. In this case, the 4 and the 6.
Okay, 4 and 6 are the means.
The extremes are the numbers sitting on the far outside edges, the 3 and the 8.
Means are in the middle, extremes are on the outside edges.
And here is the fundamental unbreakable rule of proportions. In a true equal proportion, the product of the means always equals the product of the extremes.
Oh.
When you multiply the middle numbers together, they must equal the outside numbers multiplied together.
Okay, let's unpack this. Rushing through the terminology is where I usually get lost. We need to talk about how you actually solve that on paper at the bedside, which is a process called cross-multiplying.
Yes, cross-multiplying.
I think doing this conceptually with fractions makes the most sense. When you write these ratios as fractions, one next to the other, you are going to draw an imaginary x through them to multiply them.
Exact.
No.
Spot on.
You multiply the top left numerator by the bottom right denominator. Then you multiply the bottom left denominator by the top right numerator. Let's walk through a concrete clinical scenario rather than just abstract numbers.
Let's do it.
Let's say you look at a vial of liquid medication. The label says there are 5 milligrams of drug in every 1 milliliter of liquid. That is your known ratio, 5/1.
Okay, 5/1.
Now, you look at the doctor's chart. The doctor ordered a dose of 20 milligrams for the patient, but the doctor didn't tell you how many milliliters of liquid to draw up into the syringe to get that 20 milligrams. That unknown volume is your x. So your second ratio is 20/x.
So we have two fractions, 5/1 and 20/x. And as a nurse, there is a golden rule for setting up your dosage calculation proportions on your scratch paper to avoid getting confused.
What's the rule?
You always place your half fraction on the left side of the equal sign. That is the known ratio, the concentration of the medication you are physically holding in your hand. So the 5/1 goes on the left.
Right. Makes sense.
Then you place the ordered fraction on the right side. That is the dose the doctor requested where you are trying to solve for x. So the 20/x goes on the right.
Have on the left, ordered on the right.
Before you even think about doing the math, you must verify that your units match and are in the same sequence on both sides. If your half fraction is set up as milligrams on top and milliliters on the bottom, your ordered fraction must also be set up with milligrams on top and milliliters on the bottom.
Oh, that's important.
If they don't match, say, one is in grams and the other is in milligrams, you have to do a conversion first.
But in our scenario, they match. Milligrams over milliliters, 5/1 equals 20/x. So we cross-multiply. We take the top left, which is 5, and multiply it by the bottom right, which is x. That gives us 5x.
Then you do the other side of the x.
Right, so the bottom left is 1, multiplied by the top right, which is 20. 1 times 20 is 20. So now our equation is simply 5x equals 20. To get x by itself, we divide both sides by 5. 20 divided by 5 is 4, so x equals 4. You need to draw up 4 milliliters of liquid into your syringe to deliver the requested 20 milligrams of medication to the patient.
That is the core of bedside math. You are taking the physical reality of the vial in your hand and balancing it against the doctor's order, using a proportion to find the safe volume to administer.
But the reality is, a nursing shift is chaotic. You aren't always sitting in a quiet room with a calculator. Which brings us to the next section, the bedside toolkit.
The toolkit is vital.
Doing the cross-multiplication on paper is essential, but as a nurse, you also need to understand the physical tools and standard measurements you will encounter during a shift. You have to translate those written numbers into the physical world.
Very true.
Let's run through some of the most practical bedside conversions you will need to rely on. First up, intake and output tracking, known as I and O. Patients drink out of standard cups measured in ounces, but the hospital requires you to chart their intake in milliliters.
Right, and the standard conversion here is that 1 liquid ounce is equal to 30 milliliters. Rather than using complex formulas, this is often just quick mental math.
Yeah.
If your patient drinks a standard 8-ounce cup of water or juice, you multiply 8 by 30 in your head, which means you document 240 milliliters of intake.
1 ounce is 30 millioil, 8 ounces is 240 millioil. Got it. Next is temperature. The hospital uses Celsius, but many patients, and even their families, only understand Fahrenheit.
The hospital uses Celsius for the same reason we use kilograms. It standardizes the data and prevents charting errors.
Okay.
A normal baseline body temperature is 37.0 degrees Celsius, which is 98.6 degrees Fahrenheit. When we are assessing a patient for a fever, the clinical threshold is typically 38.0 degrees Celsius, which translates to 100.4 degrees Fahrenheit.
If a family member tells you the patient had a fever of 102 degrees Fahrenheit at home and you need to chart it in Celsius, there's a specific formula. You take the Fahrenheit temperature, subtract 32, and then multiply that result by 0.5556 to get your Celsius reading.
Good to know, yeah.
But honestly, most modern hospital thermometers do this conversion for you with the push of a button. However, one tool that won't do the math for you is the syringe you are holding.
And understanding your equipment is vital. A milliliter is the exact same volume as a cubic centimeter, so 1 ml equals 1 cc. You will hear seasoned nurses and doctors use those terms interchangeably on the floor.
Good tip.
When you are looking at standard syringes in the supply room, they usually come in 5 milliliter or 10 milliliter sizes, and they are marked with tiny lines indicating 0.1 milliliter increments.
But insulin and tuberculin syringes are a completely different ballgame, right?
They are. You can never swap them out. An insulin syringe is measured in units, not strictly in milliliters. 10 units on an insulin syringe equals 0.1 milliliters.
Okay.
And TB syringes, which have a total volume of just a single milliliter, are designed for incredibly fine, high-stakes measurements. They measure down to the 0.1 and even the 0.01 milliliter increment.
Wow, that's tiny.
Yeah, if you calculate that a neonate needs 0.45 milliliters of a medication, you cannot measure that accurately in a standard 5 milliliter syringe. You must use a smaller syringe designed for that level of granularity to ensure the patient doesn't get an accidental overdose.
Here's where it gets really interesting. You've weighed the patient, you've converted pounds to kilograms using your 2.2 rule, you've identified your halve ratio on the drug vial and understood its concentration. You've set up your proportion with the ordered dose on the right, you matched your units, and you successfully cross-multiplied to solve for X. You even grabbed the correct TB syringe to measure it out. But what if you look at that final dose in the syringe and a voice in your head says it just feels like too much liquid?
Ah, that intuition.
Right. What if you still aren't 100% sure it falls within a safe therapeutic range for your patient?
If we connect them to the bigger picture, it all comes back to the nurse's ultimate responsibility. Calculating the math flawlessly on paper does not absolve you of the responsibility of verifying the clinical safety of the dose.
That's a great point.
Math isn't the final step. Your clinical judgment is. Sometimes a doctor might write an order for a total daily dose of a medication, but physiologically, that massive dose needs to be divided up and given over several smaller administrations throughout your 12-hour shift.
Oh, definitely.
If you just draw up the total daily dose all at once, even if your math is flawless, the administration is deeply unsafe.
So what do you do if you are second-guessing your calculation at the med cart?
You stop. You do not push that medication.
Yeah.
If the safe therapeutic range is not explicitly listed on the medication label or the chart, you must look it up. You can consult the clinical pharmacist. They are an incredible resource, and they love answering those questions.
Always check with pharmacy.
Definitely. You can check the medications package insert, look it up in a physician's desk reference, or use the hospital's internal digital pharmacy resources. You always double-check your work. You are the last line of defense before that medication enters the patient's body.
It is so important to hear that. Asking for help or double-checking a reference is never a sign of weakness. It is the mark of a great, safety-oriented nurse.
100%.
Let's do a quick mental checklist to lock in these key takeaways. The next time you step up to the med cart, visualize these steps. First, master the 2.2 rule. Divide pounds by 2.2 to get kilograms, which is the global standard for weight-based dosing to prevent massive errors.
Right.
Second, remember that ratios represent the concentration of the liquid. The numerator is the drug. The denominator is the solution. The bigger the denominator, the more diluted the drug.
Spot on.
Third, to find your final dose, set up a proportion placing the medication you have on the left and the dose ordered on the right. Ensure your units match, and then cross-multiply the means and the extremes to solve for your unknown volume.
And remember to always choose the appropriate syringe for the volume you just calculated.
Keep practicing these steps. The math phobia will fade the more you do it, and soon it will just become muscle memory. Keep learning with Lecturio, keep reviewing your bedside conversions, and you are going to be a fantastic, confident nurse on the clinical floor.